So hello everyone. So in the last session we have started with the fourth module, right? That is stability analysis, and also we have discussed the basics of Routh-Hurwitz's criteria, its statement, and how to represent the characteristic equation in the form of a Routh array. Okay, when the system is said to be stable, unstable, and how to check the values of the Routh array, how to calculate it. We have seen that those things. Okay, so here in this video we are going to discuss few more cases or the special cases of this RH criteria, that is Routh-Hurwitz criteria. Okay, so now what are the special cases? Let's see. While calculating the Routh array we would be getting some of the conditions. So now let's analyze these conditions. Okay, so case 1, so the first element of any of the rows of the Routh array is 0, and in the same row the remaining elements are not 0, at least one non-zero element. So now what is this statement say? So for that, in order to understand this statement, let's take one simple characteristic equation as an example. Okay, so here I have taken this characteristic equation as an example, that is s to the power 5 plus 2s to the power 4 plus 3s cube plus 6s square plus 2s plus 1. So represent this in the form of a Routh array. So here again first write all the degrees of s, that is s power 5 up to s power 0. Draw one table here, and after that write the coefficient of s power 5 first, that is 1. Then skip one term and write the coefficient of s cube, that is 3. Then skip one term again, write the coefficient of s, that is 2. Then skip one term, then again after 1 we don't have any term, so this is 0. Same thing for write the coefficient of s power 4. Skip one term and write the coefficient of s square, and skip one term and write the coefficient of s power 0. Okay, that is 1. Again we have no term here, and after that what we need to be doing, we need to be multiplying in order to calculate the third row first element. Use the previous second rows, that is first two elements, that is 2 into 3. First we need to be multiplying this. Okay, 2 into 3, not this 1 into 6 first. 2 into 3 minus 1 into 6 divided by 2, that is 2 into 3 minus 1 into 6 divided by 2, that is 6 minus 6 by 2, that is equal to 0, right? So here when we calculate the first element, what we are getting, our answer we are getting it as 0. Okay, so this is one of the special case. Okay, whenever we get, after solving this, whenever we get our first element, or in the first column, if we get from any row the first element answer as 0, our Routh test fails. Okay, we cannot get, it's a rule that we cannot get the answer, we should not get the answer as 0 in the first column whenever we calculate the Routh array. So what happens if we get the answer as 0? Okay, so suppose, see here I've got the answer as 0, and here I've got the answer as 3 by 2 by calculating 2 into 2 minus 1 into 1 by 2. Here I've got 3 by 2 and I've written 0 0. So here now we have got all the elements of third row. So now after, if you want to calculate the elements of fourth row, we need to be using the second and third row, right? So let's see what we will be getting the first element here. So 0 into 6 minus 2 into 3 by 2, that is 3, divided by 0, right? So 6 zeros are 0 and 3, minus 3 by 0. Minus 3 by 0, anything by 0 we would be getting it as infinity, right? So that is invalid, we cannot represent the term infinity. So here in order to calculate the fourth row elements, all the terms we are getting here it as infinity only. So that's why this Routh test fails here in this case. Okay, so now how to avoid this kind of problem? Okay, so what we need to be doing is, so whenever we get the whenever we are arising with this problem, we have the solution for the, we have two solutions for this above effect. Okay, so now let's discuss those two solutions. What are those two solutions? Let's see. So this is the solution 1. What we need to be doing is, so I have taken the same Routh array, and here what I've done is, I've got here the term as 0, right? We need to replace this 0 by epsilon. Okay, epsilon, and so this method is named as epsilon method. Okay, so whenever we get this kind of problem, what we need to be doing is, if we got the our first element answer as 0, convert it and replace that term by epsilon, and taking that epsilon term only do the further calculations. Okay, so here see I've taken epsilon, and here again the same answer 3 by 2 I have got. So now in order to calculate this term, I have to multiply these two, that is epsilon into 6 minus 2 into 3 by 2 divided by epsilon. That's why I got here 6 epsilon minus 3 divided by epsilon. Okay, so I will write this term as it is, don't go to simplify it or something, write this term as it is. Then after that calculate this term, that is epsilon into 1 minus 2 into 0 divided by epsilon, that is epsilon by epsilon, that is equal to 1. So I have written here it as 1, the next element. Okay, so the same thing again, using the third and the fourth row, try to calculate the first element of the fifth row, that is cross multiply these two terms, 6 epsilon minus 3 by epsilon into 3 by 2 minus epsilon into 1 divided by this term only. So after simplification, this is our answer what we are getting, that is 18 epsilon minus 9 minus 2 epsilon square divided by 12 epsilon minus 6. Okay, then again the second element of that row is equal to 0. Then after that again multiply the fourth and fifth row, use those fourth and fifth row and try to get the answer of the last element. Again cross multiply these two terms and get the answer as, and here I've got the answer as 1. Okay, after that what we need to be doing is, wherever we have taken epsilon, right, we need to be taking the limits for that. Okay, avoiding the first term, that in place of 0 we have taken epsilon, right, avoid that, and rest all the terms which I have got, right, for the first column, that is 6 epsilon minus 3 by epsilon and this term. For those two terms we need to be taking limit, that is limit epsilon tending to 0 and that term, that is 6 epsilon minus 3 by epsilon. Okay, then apply the limits for that, that is split this term, that is 6 epsilon by epsilon minus 3 by epsilon, so this 2 gets cancelled. 6 minus 3 by epsilon, the value of epsilon is 0, 3 by 0, so 6 minus infinity, so our answer we are getting it as minus infinity, right, after we substitute the limit epsilon tending to 0. The answer is minus infinity, so that's why I have striken off this term and written it as minus infinity. Okay, same goes with this term. Okay, so here again same, take this term and take limit epsilon tending to 0, write this term. So here epsilon is 0, so this term gets cancelled, this term gets cancelled, and also this term gets cancelled. So our remaining terms are minus 9 by minus 6. Our answer is 3 by 2. So I have striken off this term and I have written it as 3 by 2 here. You can see it, 3 by 2. I have written it here, I am highlighting it, it's not visible. I have written it 3 by 2 here. Okay, so 3 by 2, 0 and 1. So this is the whole method of epsilon method. And after that again the same thing, check the sign changes of the first column. Okay, that is, so here we have from plus from plus epsilon. So here in the x square term we are getting our answer is minus infinity, right, minus infinity we are getting. So plus to minus there is one sign change, and again from minus infinity we are getting the answer as 3 by 2 plus 3 by 2, so minus to plus there is one more sign change. So we can say that this particular characteristic equation is having two poles, and also the system is unstable and it lies on the right half of the S plane. Okay, since the system is unstable. Okay, so in this way we can avoid that Routh test in order to fail. This is one method. So we have one more method, that is replace S by 1 by Z. Okay, wherever the characteristic, whatever is there in the characteristic equation, okay, we need to replace all the S terms by 1 by Z. This is the second solution. Okay, I've again taken the same characteristic equation. Okay, first the same thing, take one characteristic equation, draw the Routh array. If whenever you have gotten any first column term as 0, then stop the calculation there. Again go to the question, write down the question again and replace all the S terms by 1 by Z. So that is here I have written S power 5 as 1 by Z to the power 5, 2 S to the power 4 as 2 into 1 by Z to the power 4, that is 2 by Z to the power 4, 3S cube as 3 by Z cube, 6S square by 6 by Z square, 2S by 2 by Z, and 1 as it is. So now here again simplify this term. Here you can take the LCM as Z to the power 5. Okay, the whole divided by Z to the power 5 is equal to 0. So after taking the LCM, we would be getting it as 1 plus 2Z plus 3Z square plus 6z cube plus 2z to the power 4 plus 1 into z to the power 5 divided by z to the power 5 is equal to 0, and if we bring the z to the power 5 to the other side, it would be multiplied by 0, so our answer here would be getting it as 0, so this term vanishes, so that's why I have not written this term here. So here again arrange this this equation in the from higher degree to lower degree, that is reverse this equation and write it down again. And now for this, so now after replacing s by 1 by z, so this is our new characteristic equation obtained in terms of z now. Okay, so now for this equation again the same thing, not much to do. Write the Routh array. Okay, and first write all the degree terms, that is z to the power 5 to z to the power 0. Here we won't be getting any term as 0 in the first column, we would be getting standard values. Okay, calculate the Routh array, all the values, and check for the first column. So how many sign changes we are having? So here again we have two sign changes, that is from 7 by 3 it goes to minus 3 by 7, there is one sign change, plus 2 minus, and from minus 3 by 7 it goes to plus 1, we have one more sign change from minus to plus. So since there are two sign changes, hence the two poles are lying on the right half of the S plane, the system is said to be unstable, right? So see, if we use both the methods, both of the methods I have used here, epsilon method and replacing s by 1 by z, we have got, in both the cases we have got two sign changes, right? But the positioning is different. So here we have got the sign change from s cube s cube to s to the power 1, and here I have got the sign change from z square to z to the power 0, right? It doesn't matter. These two methods are just to verify how many sign changes are there, whether the system is said to be stable or unstable. If the number of sign changes are equal by using both the methods, we can say that both the methods are equally the same. You can use any one of the methods. Okay, so these are the two important methods to avoid this effect. Okay, hope you understood this method very carefully. Okay, so yeah, we would be discussing one more concept now. Okay, so this is the case 2. So this case 2 says that all the elements of any row in the Routh array are 0. Okay, so now what does this mean? So for example, I have taken one simple transfer function here, sorry, the characteristic equation. Okay, that is simply I have written some terms, that is s to the power 5 4 3, and all the coefficients simply I have written. So what is this case 2 here? Case 2 means in one particular row. So here using these two rows I have calculated the third row elements, right? So here the third row elements, if one in a single row, if all the elements are 0. Okay, so what was the last case? If any one of the element in the first column after calculating the Routh array, if it is 0, we use the two methods, right? Epsilon method and replacing s by 1 by z method. So here in this case 2, what it says is, in a particular row, if all the elements are 0. Okay, if all the elements are 0 in a particular row, what we need to be doing is the procedure to eliminate the above effect in Routh array. So how to eliminate this above effect, what we should be doing? Okay, so now let's see what we should be doing. We have a few steps for that. Step 1, form an equation by using the coefficients of a row which is just above the row of zeros. Okay, such equation is called as auxiliary equation. Okay, so now what does this statement mean? So if we are getting any row of zeros, that is in all the elements of the particular row, if we are getting it as 0, we should form an equation by using the coefficients, that is these three coefficients, okay, of a row which is just above the row of 0, that is above this row of zeros we have this row, this row. So here the coefficients are D, E, F. Okay, and such this equation here, after writing the equation, that equation particularly is called as auxiliary equation, and here I have written that auxiliary equation, that is D into the coefficient is s to the power 4, right? And after that E into, I told you, right, we need to be skipping one degree, that is s cube is skipped, and here we need to be writing is that E into s square plus f into s to the power 0, right? One more degree I have skipped it. So this is our equation, that is ds power 4 plus es square plus f equal to 0. Okay, understood till this much? So here whenever we get the row of 0 element, just above that row of 0 element, use its coefficients and form an equation using those coefficients, and that equation is called as auxiliary equation. Step 2 is we need to take the derivation of the auxiliary equation with respect to s. Okay, so that is whatever equation we have got here, let's take its derivative. So the derivative of ds to the power 4 is 4ds cube, and es square is 2 into e power s plus f. This is a constant, so f is 0. So this is the derivative of this auxiliary equation. After taking the derivative of this auxiliary equation, the step 3 says that replace row of zeros by the coefficients of the above equation. That is, whatever the coefficients we get after taking the derivation of the auxiliary equation, that is 4d and 2e, okay, we need to replace the row of 0 by the coefficients of the above equation. That much, that's all. So here again they rewrite the Routh array, that is a, b, c, d, e, f. So in place of coefficients of in place of row of zeros, that is 0 0 0 we had, right? So in place of that, write the coefficients of whatever the derivation we have taken, that is 4d and 2 power 2 into e. So I have written it 4d and 2e. Same thing, whatever coefficient we got, write it and go on solving the Routh array. That is, complete the array in terms of these two coefficients. So we would be getting the solution for the Routh array. Okay, so this was all about the second case. Hope you have understood this. That is, again, once again I'll summarize. So whenever we have a row of zeros in a particular Routh array, just above that row of zeros, take the coefficients of that, form an equation, that and that particular equation is called as auxiliary equation. After that, take the derivative of that auxiliary equation, and whatever the coefficients we obtain from that derivative taken, replace that row of zero elements by those coefficients and continue solving. Okay, so this is one more special case. So these were the two important cases which we obtained during the solving of the Routh array for the stability of the control system. So we will be discussing now one more simple concept. Okay, so now let's see that. The next concept here is marginal K value and frequency of sustained oscillations. Okay, so now what does this marginal K value mean? So now let's discuss this in briefly. So the marginal value of K is that value of K for which the system becomes marginally stable. Okay, marginally stable means not completely stable or not completely unstable. It would be lying between those two stable and unstable states. So that is called as marginally stable state. Okay, for a marginal stable system, there must be a row of zeros occurring in a Routh array. Okay, this is one condition, that is, for a marginal stable system, there must be a row of zeros occurring in the Routh array. So the value of K, which makes any row of the Routh array as row of zeros, is called the marginal value of K. Okay, so the value of K which makes any row of the Routh array as row of zeros. For example, if we got one term that is in terms of K, so I am writing one simple term, that is 6K plus 5 divided by 4, something like this I am writing. So, and the rest of the two elements we are getting it as 0 and 0 in a particular row. Okay, if we want this to become row of zeros, if we want this to become row of zeros, what we should be having, that is, this K value should be equal to 0, right? Whenever this K is 0, so this whole term would be 0 and would be occurring as the row of zeros, and that value of K which make the Routh array as a row of 0 is called as the marginal value of K. Okay, so that is this term. If we make 6K plus 5 by 4 equal to 0, so what we would be getting, 4 zeros are 0, so 6K plus 5 equal to 0. 6K is equal to minus 5, so K is equal to minus 5 by 6. So this value, whatever we get as the K value, so this value here in general is called as the marginal value of K. Okay, so generally if K is equal to 0, if it makes the row of s to the power 0 as the row of zeros, that is the last degree term, that should never be equal to 0. Okay, so if K is equal to 0, the system cannot be the marginal value of K. That's one condition, because for K is equal to 0, the constant term in the characteristic equation becomes 0. Okay, that is, for example, s cube plus s square plus 2s plus K. Okay, this is one constant, right? I've taken it as K equal to 0. If we make this K is equal to 0, this whole term vanishes, and here we would be remaining only with these three terms, that is s cube s square plus 2s is equal to 0. This is not but a standard characteristic equation which is represented in the Routh-Hurwitz criteria. It should always consists of the coefficient of s cube coefficient of s square, coefficient of s power 1 and coefficient of s power 0. Okay, it should be considering this last coefficient cannot be equal to 0 in order to satisfy the Routh-Array condition. Okay, Routh-Hurwitz condition. So that's why k is equal to 0 cannot be the marginal value of k. So it becomes 0. That is one coefficient of s power 0 vanishes, which makes the system unstable instead of marginally stable. Okay, so whenever if we get this kind of condition, the system is directly, we can say that the system is unstable instead of marginally stable. So therefore the value of k should always be greater than 0. Okay, so this one condition you should keep in mind. So again the same thing I've told you, note that is marginal value of k is that value of k which makes any row other than the s power 0th row as the row of zeros. Okay, leaving the last row, that is s power 0, which we are getting, that row should not be equal to 0. Leaving all those things, the other row, any of row of zeros, if we make it as 0, we would be getting one marginal value of k. Okay, so now to obtain the frequency of oscillations, we need to solve the auxiliary equation. Okay, a of s is equal to 0 for the value k is equal to k margin. Okay, so this would be seeing in detail while we solve the problem related to this. Okay, so we'll see that later. So the magnitude of imaginary roots for a of s equal to 0 obtained for marginal value of k indicates the frequency of sustained oscillations which system is going to produce. So this thing till here to here we would be discussing while solving the problem. Okay, so yeah, that's all for this session. Hope you understood the concepts very well, all the special cases of Routh-Hurwitz criteria. So from the next few sessions onwards, we would be solving very important problems. I guess nearly 5 to 6 problems we are going to solve, and we are going to wind up this topic of Routh-Hurwitz criteria, and we would be going with the very important concept, that is Root-Locus. Okay, in a few sessions, after some of the sessions. So that's all. Please like, share, subscribe, and you can refer our playlist here. We have solved all the model paper solutions, so it would be appearing on the right of your screen now. So please refer those playlists and refer the solutions for all the model papers for all the subjects. Okay, we have for all the subjects: control system, electromagnetic theory, principles of communication, and microcontrollers. We would be updating all of them. So please be tuned to this channel, hit the notification bell and be updated. Like, share, subscribe. Thank you.